So, hey everyone. As Alfred said, my name is Chris Sullivan. So today I want to give you a performance tour through the NVIDIA Blackwell bring up in Triton. This talk is for Triton kernel developers and for Triton compiler developers, and really especially the individual who finds themselves popping back and forth between those roles, which I think is a common paradigm in Triton development. So I'm going to share a few patterns and some pitfalls having used Triton with Blackwell, but also some great tools we can use to course correct. But first, before I go into that, huge thanks to this incredible list of collaborators. This work was done by a big group, and it couldn't have been done without this amazing village. So many thanks to all of them and to this community for such an incredible ecosystem. So let's dive in. I'm going to tell you about 4 specific aspects of Blackwell that are brought to Triton. 1, NVIDIA's 5th generation Tensor Core. 2, the Tensor Memory Accelerator. 3, block-scaled matrix multiplication. And 4, warp specialization. And I'll end with a Blackwell Triton roadmap. But in each of these, I want to help you, I want to weave a narrative with how each of these 4 aspects impact a real-world workload, Triton's mixture of experts kernel. Phil mentioned this. It's been brought into the Triton repo recently. It's used by GPT-OSS. It's used in large language model serving. It's an incredible workload. It also provides a really interesting litmus test for how effectively we're bringing in these 4 Blackwell features into Triton. So this will be a journey through performance and give you a little bit of an idea of what's going on under the covers in bringing Blackwell support in Triton. So let's start. NVIDIA's 5th generation Tensor Core brings twice the throughput relative to Hopper's 16 and 8-bit data types. It introduces a new level of memory hierarchy called tensor memory, which effectively replaces our register memory for Tensor Core input and output. That means our accumulator lives inside of tensor memory. And critically, that helps us decouple the MMA engine, the Tensor Core, from the SIMT core. So these now can operate fully asynchronously. And I guess the beauty with Triton, as you heard in the last talk, is that really with Triton language dot, we really need no changes. If you take your Hopper out, plug your Blackwell in, you get all of the Blackwell performance I've highlighted in this slide. The second aspect of Blackwell I want to talk about is the Tensor Memory Accelerator. So also mentioned earlier today, and I think it needs one more underline, is that Triton recently graduated its Tensor Descriptor API into the core language. That has provided really featureful, full feature support for Blackwell's Tensor Memory Accelerator. We are able to do host and device tensor descriptor allocations. Host for ahead of time allocation for high performance, and device or kernel runtime for scenarios when you need to have a little bit more flexibility or you have runtime decisions you need to make. It supports loads and stores up to 5D in Blackwell TMA. Of course, the Triton API is, I think, ND. It's agnostic. Also, rather importantly, especially for this mixture of experts layer, which we'll dive into next, is that Triton supports Blackwell's fuse TMA gather and scatter modes of operation. So what is that? I will follow that up in just a few moments. So we've talked about 2 aspects of Blackwell. I think we have the base ingredients we need to understand this Triton mixture of experts kernel that's in the repo that I mentioned. A common MOE architecture is just shown on the screen here. So it has your list of tokens that are coming in, a router mapmul which routes to different experts, a gathering step which gathers those tokens to each of the experts that are going to operate over them, an activation, another fully connected layer, and finally a scattering step, effectively the reverse of the gathering step, sending back out the superposition of all of your weighted token components from each expert, and then reducing over those to get your final output. Triton optimizes this mixture of experts layer by fusing together the gather in the fully connected step and the scatter in the fully connected step, and activation as well in there. So this is the key architectural innovation of this kernel, one of the key architectural innovations, and it's enabled in this way. Let's zoom in and take a look. So for the gathering and the fully connected layer. We have our tokens being routed out to these different experts. What this looks like is we have some set of tokens that are showed in these colored boxes over here. And maybe I can use this laser. There we go. And those are then routed out to interleaved, repeated, into contiguous sets of tokens that are needed for each expert. Effectively, we take them, we repeat them in global memory, we have this big activation, and then we send each of those through tensor memory loads down into SMEM, where we're going to operate on them with our MMAs for each of our experts. We get this effectively like block sparse or group gem form of the fully connected layer. But for the optimized case, instead, we can take instead of doing this global memory to global memory marshalling of each of the tokens, we can tell the Blackwell TMA, these are the indices, the rows into which I'd like you to pull into a contiguous chunk in SMEM. That then lets us have a very straightforward implementation of GEM that looks like really no different than a normal matmul. So Triton is one of the few frameworks that implements this capability, and yeah, it's pretty awesome. So these two ingredients together, I think, give us what we need to understand our first baseline of performance in this Triton mixture of experts kernel. Our baseline is going to be an FP8 by FP8 activation, FP8 activations, FP8 weights. We're using our 5th generation Tensor Core and the TMA fusion that I mentioned before, gather, scatter, fusion. And we are looking specifically, we want to look in this plot of, we're looking at roughly on the x-axis, the average number of experts or tokens per expert. So in MOE routing, of course, it doesn't necessarily, it's not going to be uniform in a more realistic scenario. It might have some stochastic, some stochasticity, or it might have a long tail. But if we assume a workload of like 128 experts, and the configuration I show here on the screen, a region of interest for large batch inference is this roughly 64 tokens per expert. That corresponds roughly to like 1 block of activations. So we're going to keep an eye on this red region as we go. But the question is like, this workload is very heavily memory bound. We have 128 experts worth of weights that we have to bring in. So we're really spending a lot of time marshalling data down into shared memory. Question is, how can we improve the performance? One way is by reducing the memory traffic. And we can do that by quantizing the weights of these experts down to MXFP4. And that's what we're going to talk about next. The third topic for Blackwell support in Triton is the 5th generation Tensor Core support for block scaled formats. That is MXFP8, MXFP6, MXFP4. Also, NVIDIA specific NVFP4 formats. Critically, we allow support for mixing the A and B operands so that we could have, for example, MXFP8 on the activation and MXFP4 on the weights. That is what we do for this mixture of experts layer I'm walking us through. It has 2x the throughput relative to Hopper FP8 for MXFP8. But for the MFP4 data types, we get to the 4x improvement over Hopper FP8 for MXFP4 and NVFP4. And the scale factors, importantly, as I'll talk about a little bit later, they must reside in in TMEM before we do our MMA. They must be in TMEM. So we have to marshal them from global memory to shared memory to TMEM. This is exposed in Triton through Triton language .scaled. It's pretty similar to the .API, having just now an additional scale factor for the activations or for the A and B matrices, as well as some type information about what format the either byte or sub-byte types are. Okay, so as I mentioned before, the Triton mixture of experts kernel that we're going to come back to now, it uses this interesting combination of using FP8 activations, but it uses MXFP4 block scaled weights. So how does this help us? Let's take a look. Okay, so with MXFP4 scaling factor in this region that we get, MXFP4 weights, we're still doing FP8 compute. We see somewhat of a bump there, but over there we're feeling a little bit more uncertain. Like what's going on at the higher batch sizes? If we pull out our Nsight compute tool and take a look, at this region, one of the things that we find is that there's actually a fair amount of bubbles or gaps in our Tensor Core execution, which we don't like. We don't want to have gaps in our Tensor Core utilization. Hopefully, or ideally, this is just running nonstop. The other thing that's sort of curious here is that we see the SM is really busy only half the time, roughly. And when it is busy, it's executing an instruction per cycle. So it's doing nothing, and then ripping through a lot of instructions, and then doing nothing again. So this is very bursty execution. What we'd like to do and like to see is less bursty. We don't want to see more overlap. Ideally, the SM busy is percentage is bigger, and the rate of instructions when the SM is active is lower. So one of the ways, the question is like, how can we go about improving the overlap? And like to put words on this is like, how can we improve the instruction level parallelism? So to understand a little bit better about one way in which we can do that, the method I want to tell you a little bit about is warp specialization. But I want to build up to an intuitive understanding about what warp specialization is. I know there's a lot of experts here who know and have worked with warp specialization a lot. And so, and maybe, maybe this won't be helpful for you, but hopefully for those who are less familiar with it, we can bring you online with warp specialization. So to start, let's go back to some of the GPU core basics. So, sort of in the beginning, there was this warp scheduler. The warp scheduler allows us to have fast and free instruction level parallelism by dynamically swapping between warps. If a warp is stalled, we have the instruction scheduler, or the warp scheduler, to pop over to another warp that's ready to go. So in this world, we have one warp that does blue loads, red MMAs, and yellow epilogues. And each warp gets a different work item. So warp 0 gets work item 0, warp 1, work item 1, et cetera. And then the warp scheduler starts by scheduling, running through each of the warps and issuing the first set of instructions that can be issued. And if there's any blocking, then it swaps to a new warp. And at some point through this execution, we find that we have some overlapping of loading and compute. And eventually, we have overlapping of our epilogue, our stores, our loading, and our compute, all in a sort of dynamic hardware pipeline. So this is the warp scheduler, as I mentioned, and the dynamic pipelining. Circa 2020, or around like Ampere timeline, and then also in Hopper, we found that actually there's not enough work to really be effectively overlapping. Actually, maybe another way of saying this is, we would like to see instruction level parallelism not only between warps, but we'd like to see it within a warp as well. So for like Ampere and Hopper, one of the things that we found can be quite helpful is to take more work and pull it into a single warp or into a single warp group and use what we call persistent kernels. What I showed before was non-persistent kernels, where we have each warp needing to perform one work item, kind of wake up and go to sleep. That's the wave quantization effect that some of the prior talks have talked about. Well, in this talk, or in this particular section, we're talking about how do we interleave instruction level, or interleave instructions within one big warp. So this is a concept known as software pipelining, persistent kernels. And I guess maybe I should just pause here for a moment and say, if you haven't seen Pavel Sashabuk's 2024 Triton conference, like if you're watching on YouTube, pause and go watch that. Because that's a fantastic overview of the pipelining persistent kernels. But when you come back to this talk, I want to just kind of give a cartoon feel for how pipelining persistent kernels works, but also some of the challenges that are there for bringing performance. And the basic crux of this cartoon is that in this PowerPoint drawing of what software pipelining looks like, we've taken all of these work items and we've overlapped them sort of like perfectly in the picture. And you've got to, but the root that I'm trying to get us to is that we effectively have one, what I call like a hero warp. This warp is doing a lot of work. It's doing many different things. It's doing the loads, the stores, and the epilogues. And the process of finding the optimal schedule is sometimes called schedule linearization. You kind of have to come up with what the right schedule is. And for Ampere and Hopper, this was, I would say, a rather successful technique, though there were some edge cases in Hopper. And Triton has, as you've heard several people say, has developed a really generic core infrastructure for software pipelining for the transformation process, though not all of that capability is yet exposed to the user from the Triton front end. And so what I want to say is, like, when you first start, like in my cartoon, I show one example of what could be a schedule linearization, something like this. And that gives you your like baseline performance. And in the cartoon, we see a little bit more like, actually, you can get a little bit better performance if instead we focus on a schedule that looks something like this. Okay, well, that did require some non-trivial compiler changes, but we're okay with it until it gets more and more complex. And sort of eventually, you find that the optimal schedule is not easy at all for the compiler to emit, or for the user to write, to sort of contort their fingers and get out. So I think I sort of put this cartoon in just to say like software pipelining persistent kernels definitely is an important strategy, but we want to be able to do both things. We would like to ask the question of like, how can we both leverage the benefit of software pipelining persistent kernels while also better enabling the warp scheduler? Because in the story, like the warp scheduler has kind of been off in happy land. So maybe another way of saying this is like, let's bring him back. Let's bring the warp scheduler back from vacation and put these two to work together. And this brings me to my fourth topic I'd like to discuss about that is important for Blackwell performance that we've brought to Triton. Specifically, this is warp specialization. So warp specialization is the thing that's trying to leverage statically scheduled instruction level parallelism within warps. And it's also trying to leverage the warp scheduler for doing fine-grained swapping or ILP between warps. So what does this look like? In Blackwell, we have this picture again of, I guess you can't really read that font, so I'm just saying blue loads, red MMAs, yellow epilogues again. And what this looks like is now we have separate warp roles. Each of these warps are doing a specific kind of pattern, like loading or doing MMA or doing the epilogue. And that allows the schedule for this kind of compute to be very simple, right? It's just a straight line. The load warp just load, and then block until when you run out of backing buffer or backing shared memory to load into. And you have to wait until the MMA warp signals that it's done, and you can then do your next loads. So the scheduling becomes simpler here, which is great. And it's still persistent, which is great. And with Triton, as I'll mention a little later, like you can still do software pipelining within one of these warps if you'd like to. If you had it, for example, I've shown you very simple like warp partitioning here. But you could do more inside of each of these warps if you wanted to. So you can achieve both of these things, and you don't have to worry too much about this complex schedule linearization. So again, we have our happy warp scheduler back at his desk job, making progress through each of these independent roles. And you see that you can get dynamic overlap with a warp scheduler in the same way as we saw in the original picture. So what does warp specialization look like in Triton? Today, if we have this tiny, I know it's tiny, but we have this small Triton program. It's doing just loads and a dot, and then after its K loop, it stores. We just add warp specialization equals true. And that then tells the compiler to use its automatic warp specializer to introduce the following things. Mainly, first step is partitioning. Partitioning, to understand, it's not unlike tiling. So tiling is trying to take up some input tensor and break it up into a bunch of different work items, build a work grid out of it. Well, partitioning is saying, here's this sequential program, or sequential statements in a loop. How should we assign them to different warp partitions? So this is, in that way, as you assign them, like the search over the possible partitionings is kind of like a search over, the auto-tuning over like a tiling space. It's not dissimilar from that. And once you've done your initial assignments, either automatically through your heuristics or manually through some programmatic hints or other implementations, you then propagate those assignments out. So the second step here, I want to say, is the transformation. Transformation is the part where you've taken the partitioning assignments and you introduce, in the in the Triton GPU dialect, we introduce warp specialized ops. These ops are effectively the high-level ops that are managing the producer and consumer relationships between different partitions. That's things like how to multi-buffer the shared memory and the tensor memory, and then how to do the signaling between the producers and consumers. And then we specialize the loops, like repeat them into each of the different warp partitions as a final step. And I'll just maybe make one note here is that the key focus of Blackwell automatic warp specialization so far has been more on this first part, on partitioning. Sorry, on the second part. I said the first part, I meant the second part. On transformation. We have been very careful at trying to make the mechanical process of taking any partitioning and lowering that down into a warp specialized program. And less time has been spent on finding like the optimal automatic partitioning. And you know, as you've heard today, like this isn't an easy problem either. So you know, I don't mean to like give you the snake oil and say, hey, we solved like schedule linearization, but now we have this whole new set of problems. We do have, I would say, a trade-off in low-level control and how much we're going to do in an automated way for the user, so the user doesn't have to think about this level of control. So there is a problem, but it's a different set of problems. We actually gain a fair amount of performance from warp specialization. And so now, like, let's just bring us back to the mixture of experts layer we were looking at before. So we had this problem where we were having the memory footprint of the weights on the experts. We saw a good bump. There was a reasonable bump, but for our region of interest, but we saw this like sort of drawdown. When we use warp specialization, it's better. We like to see that. We like to see an improvement in the region we care about, and we also don't see any degradation anymore. And critically, like the Tensor Core bubbles are less. We see that the SM is now busy more frequently, and when it is busy, it's not executing so many instructions. And this is, you know, really one of the like sort of just like intuitive reasons you can think about this is in each Blackwell's like stage of the compute. If you think about it in software pipeline or in like a warp group, the amount of things that are happening inside that stage in Blackwell is higher, right? We're trying to do things like move data from global memory to shared memory, and then from shared memory to tensor memory for scale factors, for example. So there's more happening inside of each of these layers. And we see that, again, like I said, we're doing less work now, which is good. So we see more overlap, less bursty, but there's still some bubbles. And there's, you know, there's also some performance, there's still some bubbles in the Tensor Core, and I'm not showing it to you, so you just have to believe me, but there are, and we don't like that. And also, we don't like the performance cliffs, which you kind of see at these powers of 2. So we'll talk about both of those things. So as I'm like looking through the next like set of things, optimizations that this kernel has brought, I mentioned before, like there's this really interesting like use case of fusing the activation, like Swigglue in this case, but I think any activation is fine. It's all the same. That's not really going to help the Tensor Core utilization, but it should help the higher batch size cases. And epilogue subtiling is something that also is not going to help that main loop performance, but it is going to help overlap those stores back to global memory and overlapping those with perhaps the loads from the accumulator, loading the accumulator from TMEM back into the RF. And so when we do both of those things, we see a nice bump in performance for the higher batch sizes, which is good, but we're still like not so happy about this region. We'd like to see some more uplift here. We don't really see a change here. This kind of makes sense. Like, probably for the smaller batch sizes, that like output tile is staying hot in L2. And so we don't benefit a lot from fusing the activation. And like I said, the epilogue subtiling, we don't expect to change the main loop performance too much. What can improve this more? And back to warp specialization. Improving the warp specialization can. And I don't have a ton of time to go through all of the ways in which you know, we did this. I basically spent maybe looking at the 3 or 4 months over the summer and counted up to 16, at which point PRs, at which point I sort of stopped because it was a lot, already a lot. Several of those PRs all of those PRs are improving the warp specialization. Some through improving the partitioning. Some are improving the partitioning and also the register allocation in each partition, which is going to help for like long scoreboard stalls. You're not stalling on registers that you need in order to perform your operations. And then another, like I would say, really interesting, and as I mentioned this briefly before, is like a key component of this is that Triton supports this novel unified architecture for pipelining and warp specialization. It allows these to be done together. And so, you know, I'd say I give you this list of several things. You can see through them together that is helping raise the ceiling for our performance overall for more or less all batch sizes in this, you know, per expert batch size, I should say. Finally, the remaining question, we have is why these big dips? Why do we see these dips after powers of 2? It'd be better if this was less. Now, the powers of 2 performance that we see in this mixture of experts layer, like they're not really common to, or they're not really uncommon. It happens, I would say, regularly, that when you move beyond a factor of 2 or outside of like the bound of a tile size, the amount of extra compute you're doing relative to the load is changing. The intensity is changing. So these big dips often indicate something about the ratio of the amount of compute you're doing relative to the amount of the memory you're moving. So you can't always get rid of these because of just of an intensity issue, or arithmetic intensity issue, but we can make them less troublesome by optimizing the memory subsystem. And I'll just briefly go through here and say, like, we did this. One of the ways we can do that is by revisiting the tensor memory accelerator. And when we go, in order to do that, we kind of take a tour back to tutorial 10 for Blackwell. Specifically, this was the Blackwell block-scaled matrix, or actually I should say tutorial 10, the block-scaled matrix multiply. And some of the learnings that we had from that, this plot that I'm showing here is when we hold everything constant except for the way in which we're moving data from, moving the scale factors from global memory into shared memory. That's the only thing that's happening in each of these bars. So the black bar is when we say we're gonna move the scale factors for the activation and weights using CPA sync or LDGSTS. Then we say let's move to using 4D TMA, and this is for MXFP4 scale factors, or scale factors used for MXFP4 compute. 4D TMA is kind of equivalent. It's a little better. 4D host, that was with device TMA. With host TMA, we see a reasonable bump here. This is primarily because we're not, the allocation of the device descriptor is not happening at runtime. It's now happening ahead of time. And finally, the best performing result we can see is if we use a 5-dimensional layout with host TMA for these scale factors. This 5D layout basically rearranges the scale factors in a way that hits a full cache line in the GPU. So we see a 40% uplift in this tutorial. And this is for an 8K by 8K by 8K gem. This is a compute-bound gem. So 40% uplift for just how we changed moving the scale factors. So that tells us probably in our memory-bound use case is going to help well as well. So when we do this, we optimize the scale factors memory layout. We use host TMA for everything. We see a nice rounding out of our dips. So I feel better about this. Looking at the Tensor Core utilization, there's not as many gaps, so that's good. We see roughly a 1.7x improvement from where we started, which is also good. And again, we're still, in this entire process, we're still just using FP8 Tensor Core, but we're using this automatic acceleration of the dequantization of MXFP4 weight in the part. So we're getting 1.7x from just using this better, lower precision expert weight. So just going to slowly wrap up with a Blackwell roadmap and some things that we want to bring into Triton, remaining things. One is we want to introduce cluster launch control. This is Blackwell's accelerated support for the ability to do dynamic scheduling of an SM's work items. So you can have a persistent kernel with some static set of things that you're doing, and then you finish those things and you can dynamically fetch more from the grid. So maybe you only do 1 or 2 items at a time, and 2 items statically, and then the rest you work steal from the GPU grid. That helps in like distributed environments or environments where you might have multiple streams that are landing on a single SM. And one SM gets blocked, it gets context switched over to doing it like a nickel kernel, for example, in an all-to-all or something like that, in distributed expert parallel form of this MOE. So this avoids the long pull SMs by allowing those SMs which are switched off doing something else to not have to be doing a long queue of work. Instead, they're swapping over to, their peers are picking up their leftover homework, or however you want to say it. Finally, another really important part of Blackwell performance is 2CTA mode. You heard Thomas mentioned earlier. We would like to bring full support into Triton for Blackwell 2CTA mode. And for this particular layer, I expect this is going to be helpful for a couple of reasons. One is if we use 2CTA TMA, that's going to mean, in principle, we could do fewer memory accesses, so we don't have to rely on L2 coalescing as much. And we can also have lower MMA latencies because we're doing a large, if we use 2CTA MMA, we now have a larger MMA that we're doing with lower latency for the overall workload. So this sort of rounds out our support so far. Few call outs today. I say check out Peter and Jeff's Gluon talk if you're interested in understanding a bit more low-level control. Check it out. What I should say is stick around because they're giving the talk next. And also check out my colleague Feiwen Zhu's poster on the CUDA tile IR backend to Triton that NVIDIA is releasing. It's an alternative automated way for us to do lowering, and it's like a different spot in the performance portability phase space. And they've got some really interesting performance numbers compared to Triton, so definitely check them out when you're thinking about this trade-off between automation and control. So just to wrap things up, Triton's making it easier than ever for us to access these performance-critical capabilities of Blackwell while also maintaining productivity. Phil had this nice picture of the Pareto font of productivity and performance that I couldn't help but not talk just a little bit about. And I think without Triton, we're somewhere down in this region. This is where we were living. With Triton has moved this Pareto frontier a lot. It's not just like where we are in where we are in this phase space, but it's also like where the frontier itself is. And I think as Triton developers, we have this unique opportunity to push the frontier outward in a way that is increasing the area under the curve, if you will. It has the biggest, being at this knee point gives you the biggest impact in both productivity and performance. And that's certainly important for Blackwell because we love being up here in terms of performance and productivity and having only a small. So if we can move this out further and have more performance with even more productivity, that would be great. I certainly think that we can use these orthogonals to grind out new programming models, paradigms, and for future architectures and for Blackwell. And I hope that you do as well. And I know that many of my colleagues also believe in this vision, and I'm extremely thankful to them and this work and the collaboration overall. Thank you for your attention. Happy to take any of your questions.
Hi, Mustafa Ali, Microsoft. Do you plan on looking at overlapping also all communications with MOE?
Yeah, actually, I think it is a very important topic, and we are actively looking at that using both, using NVSHMEM, and I know that a team at OpenAI with Phil and Wu Wei and others are working on this. I think there's with Blackwell, one of the things that we see is that it's unclear whether or not we want to be doing stream-based overlapping of communication and compute, and versus low-level kernel generation and overlapping with inside of a kernel. And the lack of clarity comes from the fact that we actually see a relatively good performance in both scenarios. So yes, we're interested in this in Triton. Certainly you can do more if you're overlapping with inside of the kernel than you can if you're doing in streams.
Yeah, because you would need some resources allocated to all if you're doing it in the same kernel. It's probably another warp or something, right?
Yeah.
Okay, thank you.
Yeah, thanks.
In terms of pushing the frontier for automatic warp specialization, what are some of the techniques for the future and the trade-offs? Because you said it was delicate before, so just curious if there's high expectations or no.
Yeah, I think the question is the trade-off that we have is both.
You can keep going. We're just gonna.
Oh, sure, yeah. The trade-off is between how much control we want to offer, either through something like Gluon, or if we want to offer an automated flow. And the complexity comes from the fact that with kernels like Attention, as you've seen, the warp partitioning for it, the roles themselves are a little less clear. In some cases, the optimal warp partitioning is not just a simple assignment of TMAs or just of a single MMA, since you have the two batch gems back to back. And so I think part of the process it's very iterative. It's using like tools like Gluon to find those optimal use cases, or tools like QTSL to find those optimal partitions, and then using that to like bring it back and understanding like what the better automated approach is. So, did I answer your question? I'm not sure.
Yeah, yeah.
Okay, great.
Thank you.
Yeah, thanks. Thank you.
All right, let's thank the speaker again. Thank you very much, Chris.
Thanks.